Our sun is the anchor of our world. It is a vast, incandescent sphere of plasma, so large that you could fit more than 1,000,000 Earths inside it. For us, it represents the very definition of scale and power. It is a main sequence star, a yellow dwarf, comfortably middle-aged and wonderfully predictable. But the universe is home to objects that dwarf our familiar star, objects of such staggering size that they challenge our sense of scale. One such object is the red hypergiant, Styphon, 2018. It resides nearly 20,000 light-years away, a distant beacon of immense proportions. If the Sun were a garden pea, Styphon 2018 would be a sphere over 17 meters wide. Its radius is estimated at roughly 2,150 times that of our Sun. It lives on the very edge of what is physically possible, a bloated, luminous giant nearing a dramatic and fleeting end. Let us engage in a thought experiment of cosmic proportions. Imagine in an instant we could swap our Sun with Styphon 218. The consequences would not be merely dramatic, they would be absolute. The sky would not just brighten, it would be consumed by a wall of light. Its photosphere would extend past Earth, past Mars, looming close to Jupiter. The story of our solar system, as we know it, would pivot in a fraction of a second. The moment Styphon 218 takes the Sun's place, the first agent of destruction would be its light. Though cooler in temperature, the hypergiant radiates far more total energy. Its sheer size means a luminosity hundreds of thousands of times our Sun's. For Earth, the transition would be instantaneous. The sky would blaze with an intensity that would eclipse 1,000 suns, a light carrying an overwhelming wave of thermal energy. This immense wave of radiation would herald our end. Temperatures would render the surface of our Sun seem cool by comparison. Our thin veil of gas would be superheated and stripped away in an instant. It would not burn. It would be ionized and blasted into space by photons and stellar wind. There would be no time for the oceans to boil. They would be flash vaporized into an expanding cloud of superheated steam, violently ejected from the planet. The solid body of the planet could not withstand such an onslaught. The crust would melt in the blink of an eye. Land masses would dissolve just as quickly. Even mountains would fail, turning to liquid rock. Seabeds would glow and melt. Rock would turn to lava across the entire surface simultaneously, the planet becoming a molten sphere, a glowing droplet of liquid rock and iron. Any trace of our works would vanish without a trace, a brief memory consumed by a star. The cataclysm that befalls Earth would be shared by its neighbors. Mercury, first to go, would be utterly vaporized. Rock and metal torn apart and assimilated into the star. Venus would follow, its dense atmosphere a liability blown away instantly. Its surface would sublimate, its mass dispersed into the hypergiant. Earth, now molten, would feel immense drag within the stellar envelope, its orbit collapsing like a stone into thick, fiery liquid. Mars, too, lies well within this giant. Its ices would vanish, rock would melt, and it would spiral inward. The inner solar system would be wiped clean. Then comes a second chaos: gravity. Stars are the anchors that dictate motion. Styphon 218 is vastly more massive. The sudden increase shatters orbital balance. Near-circular paths warp into plunging ellipses. Resonances break. The system becomes gravitational pinball. Smaller bodies scatter first. The belt dissolves. The Kuiper belt follows into disorder. The distant cometary shell destabilizes. A storm hurtles inward. Infalling bodies add fuel, lighting a deadly bombardment. The surviving giants begin a new, hostile journey. Jupiter's bands and spot would fade beneath searing heat. Its upper atmosphere would be stripped by fierce stellar wind. Saturn's icy rings would rapidly sublimate and vanish. The planet would bloat, then lose atmosphere into space. Ice giants would lose their colors as methane is stripped away. Exotic ices would vaporize, revealing superheated rocky cores or leading to ejection. Icy moons would melt and lose their volatiles to space. Rocky moons flare volcanically before being stripped bare. Far-off frozen worlds might briefly host liquid, then succumb to chaos. A hypergiant is not stable or long-lived. It burns through nuclear fuel at a prodigious rate. Powerful winds carry away vast mass, filling space with dense outflows. It pulsates, changing in size and brightness. At the end, the core collapses and a Type II supernova tears it apart. The blast forges and flings heavy elements, leaving a beautiful expanding remnant. This scenario illuminates the habitable zone, the region where liquid water can persist. With a hypergiant, the zone drifts trillions of kilometers away, far beyond Pluto. A planet would need to orbit about 6,000 times farther, with years lasting hundreds of thousands of hours. Hypergiant light skews red and infrared, poor for Earth-like photosynthesis. Massive stars live fast and die young, too brief for complex life to evolve. Our Sun's mass and stability set a generous, steady habitable zone. Its long lifespan gives evolution the time it needs. Its activity is modest compared to many stars, preserving atmospheres and biospheres. Its visible light is perfect fuel for photosynthesis, the base of Earth's food webs. Mass dictates orbits, light dictates energy, lifespan dictates time, a delicate dance. Change any one factor and the system collapses. Our thought experiment makes that plain. Our existence is the outcome of remarkably fine-tuned conditions. By studying hypergiants, we learn what makes a home and what makes a furnace. It is not the biggest or brightest star, nor the youngest or oldest, but it is ours. Ask yourself, how can small changes in the universe determine the survival or extinction of life? Quiet. Reflect on the fragile balances that make everything possible.